Next, we have to discuss in detail about the shear strain on the surface of the shaft. Consider a small angle of twist phi at the free end here. Notice that in this diagram, the size of phi is highly extravagant. In the reality, the size of phi is often very small. When this angle is small, the angle QPQ prime is very small, and the line PQ prime, which is this line, is almost a straight line. Then we consider this free end. At this free end, since the angle of phi is very small, the arc length QQ prime is almost a straight line, and the length is R phi. So consider this very small sector for this very small angle phi. Then you cut it in half. For this sector, since the phi is very small, the line QQ prime is almost a straight line. Then we can treat it as two right triangles. For each of them, it has an angle of phi divided by 2. Then the length of the small segment will be R times phi divided by 2. Then the length of QQ prime is given by R times phi over 2 times 2 equals to R phi. For everywhere on the surface, the shear strain of elements are the same. Or in another word, it is assumed to be the same. As what we have learned in previous tutorials, the shear strain of a material is just the angle QPQ prime. But for this very tiny angle, by using the small angle approximation, it is just tangent of angle QPQ prime. Then it equals to the length of this arc, which is R phi, divided by the length of the bar, which is R phi divided by L. But we know that phi over L is just the rate of change of angle of twist, so it is simply R theta. Notice that the shear strain on the surface is the maximum. So in case you are talking about the shear strain inside the material, then for any element located inside the material, its distance from the center of the circular prismatic bar must be less than the radius of it. Consequently, the shear strain inside the bar must be smaller than those elements on the surface. Therefore, we conclude that shear strain on the surfaces is the maximum.